So I knew that you had business that you were doing, right? So we had to have a little bit of music in order to try and get into the right spirit for this. And so what you're looking at is a picture that's now about 6 years old of National Synchrotron Light Source 2. And if you can get into your Wayback Machine and go even further back, 20 years ago, what you're looking at is a place that used to be a bunch of warehouses and railroad tracks and God knows what. And so I've had a chance to sort of think about this a little bit and wanted to try and describe a bit about this rainbow and what you imagine as being a possible thing. And so rather than doing a lot about all the technical, wonderful things that are going on, I wanted to share a bit of my perspective, having been a participant in this and having had a lot of friends who worked very hard on it. You know, how did it come to be and how did we build it and what were the kinds of things that came about in it? And so in reflecting on this, when we actually finished the project, I had some challenge coins that were struck, which I wound up giving to people who I worked with on the project and who helped me try and work on it and do better than I might have otherwise done on my own. And so I think there are not a few of them that reside in the village. And it was very interesting because it's a project, right? And so you tend to think of this as being, okay, it's all done and away we go. But of course, you don't do something like this unless you intend to use it for something. And so in fact, from the very beginning, all the way through the end of the project and on into its existence now as an operating facility, we were beginning with the end in mind. And so in this particular case, the coin actually says on it that this was the end of the beginning, because in fact, the construction was the beginning of the use of the facility. So really, I'm going to share with you a bit of my perspective on this from the last 20 years or so in which it came about. And I wanted to take the opportunity, since there were people who were from the village, was to remember particularly a couple of my friends who are no longer with us. To the left is Satoshi Ozaki, who I'm sure most people know. I don't think that NSLS-II would have been anything like what it is had he not jumped in very early, taught us how to actually run a project and how to actually make the thing work. And of course, beyond that, he made some wonderful technical contributions. He was a great friend to all of us who were in that project and was sorely missed. And more recently, Nick Simos, who was a great friend of ours, passed away. And he had some unbelievable kind of contributions to this facility. There are all kinds of things when you try and make something as stable as this machine that wind up being a problem, like the ocean, right? And the moon changing the shape of things and the wind on the buildings. All these things are pretty mundane, but they turn out to be really important. And rather than just shrugging your shoulders and trying to figure out what to do, Nick actually analyzed it, figured it out, and it's now basically become the standard not only by which we build more facilities, but by which other people build facilities that are really quiet and stable. He was a great friend. He was around the corner from me, even in his retirement. I miss him dearly. But I don't want to dwell on that. These are people who are gone, but they're certainly not forgotten. So I can give you the really quick tour of NSLS-II, right? That's the easy thing to do. And Neil actually already gave you a lot of it. It's a US Department of Energy facility, and it's for peer-reviewed science. So you can basically come and use this thing for free if you have a good idea. And it's meant for doing not just science, but for doing industrial research and also for doing education. It was really intended to be the world's premier photon microscope. That was the way that it started out, and that is what it actually is today. There's some numbers there that tell you it's a medium energy storage ring. It's actually kind of big. It's almost 800 meters in circumference. It can store 1/2 amp, which is a lot for something like this. And it could host up to 60 instruments, but today we've only got 28 of them. That's actually the most rapid build out of any facility of its sort. And we had something on the order of 1,800 users per year. This year we probably would have broken 2,000, except we had this nasty bug that started circulating and people kind of stayed away. So you could say that, and then you could say, all right, well, we finished that project, we're all done. Basic Energy Sciences really liked it. It was a top priority for the laboratory. We had good interactions with our stakeholders, everything was great. Lots of great technical capabilities amongst the team, yada, yada, yada. It was really great, did a lot of good stuff. We won a fancy award. We had a great kind of dinner that was going with that thing. It was off in San Diego. It was really nice. So the Project Management Institute thought that this was a really good project. And in fact, we won that award. And if we were in the hall, I could give my play and go off the stage and we could go and have a drink. but that's not really much of a story for you to work with, I don't think. And so you should be asking questions. You should be saying, no, wait a minute, you know, $1 billion? What's that all about? How did you actually manage to get that to come together? That can't be just all of those things put together in this nice little homogenized story that you get. What's it doing now, and where is it actually going to? So I'd like to try and give you at least a slice of that from this, rather than, you know, the really short kind of presentation that people tend to give where everything is perfect. It wasn't perfect, but it was awfully good. It was a lot of fun. So let me give you a little bit of background on how I try and do things. For those of you who are fans, my slides are kind of like the pirate code. They're more like guidelines, right? You wouldn't, really doesn't pay you to try and read my slides very much. I kind of use them to help me navigate, but I generally don't read off of them. And so they were things that we got from a lot of different places. I actually made a few of these slides, but most of them I swiped, right? So that's a good way to try and do things. And they're just a tiny fraction of what was actually produced to try and explain this project to people. Now, to help you out though, whenever I think there's something that's really important, I put it in an orange box like that. So that's a key point, both for you and for me, to try and remember what it is that I'm talking to. So why am I talking to you? And you know, a little bit about me. So kind of my perspective is informed by this notion that I had a really extended apprenticeship in engineering and manufacturing. Turns out that my parents ran a mechanical engineering firm from their home. So I got to see a lot of this sort of stuff from a very early age. Now, I'm seeing a bunch of quizzical people on the side of the screen. This is why it's good to share screen. Are we having a problem? Is something broken?
Which one is you in the picture?
Which one is me? No, I was just looking at some of the people who are on the screen here. This is why it's actually a useful thing for people to have their pictures up, because then you can see when people are beginning to look confused and lost, you can say, I must be doing something wrong here. What happened? Oh no, there's more smiling faces. So this is good. People are doing okay, at least for right now. So we'll keep going. So that was great. You know, got to see a lot of these things actually close up and in person. They had a machine shop that was down in the basement. That little thing that's up in the corner is an industrial bag closing machine. That was what my father designed when I was very little. I actually made one out of plywood when I was in the basement working with my dad at about 5. That's still for sale, by the way. That was one of the principles that I learned, because if you have a really good idea, it can be enduring. So fast forward a little bit, I got myself a bachelor's degree in chemical engineering from the University of Minnesota. Great school, happened to live there. Then I went on to get a PhD from Cornell University, also a good school. Then I came to Brookhaven National Laboratory for a temporary job as a postdoc in 1985. And somehow or another, I never got around to leaving. And I had a lot of good things that I was able to do. They let me use this brand new spiffy machine. 1982 is when NSLS turned on, and 1985 is when I arrived. Perfect timing. You couldn't do any better than that. All of the suffering that went into building the thing and making it go, that was in the rearview mirror. I just got to go there and use it. Karma's a bitch. It got back at me because I had to build the next one, but I really enjoyed working on that one. But you look at that list of things that I've done, it could easily leave you with the impression that I can't hold the job and they just keep moving me around so that I can stay out of trouble or out of somebody's hair. And I guess that's true to some level. But it also gave me quite a range of experiences, and that's kind of informed my perspective on how this has gone together and what kinds of things you might do with it. But along the way, I went from being sort of a scientist person to more like a project-y kind of person. So if you look at the picture that's down in the far right, that's just not even 2 years ago. We had a groundbreaking for a brand new cryo-electron microscopy facility, something I knew absolutely nothing about at the time, something I know a little bit more about now since we've actually built it and it's running. But my job these days is actually trying to help people understand what it is they're dreaming about and figure out how to turn it into reality. That's the joy of the job that I have. So that's kind of the background that I look at this all from. So I'm going to show you another slide, but it looks awfully familiar. But if you know, it's kind of reminiscent of the difficulties Gene was having at the beginning here. The dates didn't look like they were right, but this is actually right. This is just after we won the Project Management Institute. The picture is kind of familiar. And a lot of us who were involved in the project were asked to go and talk to people about how this project was run and how it worked and all that sort of stuff. And that was a lot of fun, and it was great. Because by any objective measure, the project was a ringing success. There's no two ways about it. And part of that was because so many people came and talked to us, or they allowed us to go and learn from them. So there is this kind of community feeling that, okay, well, if you had the benefit of somebody else's advice, you should at least share what you've learned. So we've gone around and we've shared, and often people say we're going to share our wisdom. And I'd like to say, we'll tell you our experiences and things that we learned. But if there's any wisdom in it, it's on the person who's actually listening to it. But this was actually really a good experience. So a little bit more about the facility. What we were aiming for was to have a facility that was 10,000 times brighter than the one that we were running. That's a big number, right? Sometimes people are looking for 10 or maybe 100. 10,000 is a big jump. And there are a lot of kind of characteristics that are associated with it, but it's basically to be the world's foremost microscope, photon microscope. You wanted to be able to image single atoms. It wasn't cheap. $912 million, which is actually good value for money, particularly when you consider the way we spent it. And it was the damnedest thing. We had, the economy was going to a hell in a handbasket, and we were having all kinds of problems in our country at the time. And my boss, Steve Durker, came to me and he said, "How fast can we spend money?" And I was like, "Excuse me?" I figured that we were basically going to go into the depths of a depression, and lo and behold, this thing that was for reinvesting in America's infrastructure showed up. And so they sort of right up front gave us $150 million of that budget to work with. And I don't know that I'll ever experience such a joy ever in my life again, because once you have the money to work with, it's all on you to actually make it happen. Often in these government projects, you're kind of worried about what the appropriation is, and things are going to go slower than you expected. But here was this golden once-in-a-lifetime opportunity. The American Recovery and Reinvestment Act basically allowed us to just proceed as fast as we could. There's some more characteristics about all of this thing. One of the things I love is it's 628,000 gross square feet. That's some number in meters, which means even less to me. 14 acres. It's 14.4 acres of building that we built in order to do this thing. And we actually, because we had the money up front, we were able to finish early. We actually finished it 6 months early. And because we could go as fast as we wanted to go, and we didn't make too many mistakes, we were able to add $68 million worth of scope to it. But that's, again, it's a little bit like the first introduction thing. You got to ask yourself, okay, well, how did you do that? And how why are you getting there? And so I just rely on the wisdom of Pooh here. You always get to where you're going by walking from where you've been. And so that was a good thing for us. We actually had NSLS. We knew a lot about where we had been. That informed a lot about what it was we wanted to do. So this is maybe oversimplifying things a little bit, but it is true. We had a much clearer vision of what we wanted to achieve at the end because we had such a solid foundation to begin with. So a little bit about electron accelerating machines. That's actually what a synchrotron is. Interestingly enough, they've been around since before we knew what electrons were. You've probably all seen this thing in your physics classes. Even in high school, they had Crookes tubes. Very nice kind of demonstration tool. And it was for studying what were then called cathode rays, which were actually electrons, not discovered for another 30 years or so. And it turns out if you take those electrons and you bang them into something, you can actually make X-rays. And in fact, if you were to go and have X-ray taken at a dentist, that's exactly how it works. That technology has been around that long. But there's been sort of a continuous evolution of the way that these machines work and trying to get the energies even higher and to try and make them more powerful sources. And it turns out Brookhaven National Laboratory is at the forefront of these kinds of things. Oddly enough, Brookhaven is not thought of as an accelerator laboratory. People talk about SLAC, the Stanford Linear Accelerator Laboratory, or Fermi National Accelerator Laboratory. But you can take SLAC and Fermi and TJ and add them all together, and they have fewer accelerators than Brookhaven does. We actually are a leading institution worldwide in the development and production of accelerator technology. And you've got some village residents there who could tell you all about that, I'm sure, including one that I work for, Ferdinand Villeke, who I'm not seeing on here, but I was privileged to be his deputy for a while. Mark Palmer is there as well, and he works with these short pulse sources. So there's a lot of expertise around. So I'm going to fast forward a little bit. Synchrotrons are really a very interesting kind of machine, but they didn't start being big like the one that I just showed you. They started out much smaller. You see these guys in the corner here? They're hovered around the vacuum chamber for this little tiny accelerator. It's actually made out of glass, and that turned out to be really, really important because that was the first time that they had made one that was transparent. They took that transparent chamber, they put it in the 70 MeV synchrotron, which was at General Electric at the time up in Schenectady. And they thought that there was sparking and arcing that was going on inside of the machine. And in fact, they had a machinist, a guy named Floyd Haber, go look at this thing to try and see with a mirror when there was a spark. And the place where I'm running the laser on that picture is actually synchrotron radiation coming out of this tiny little machine. And they figured that all out, and they understood what it was once they'd actually seen it. And they said, oh yeah, of course, that was particular. We should have known that that was going to be there. So at this point, you know the characteristics of the light, and you can actually figure out how to try and make it. That was mostly visible light that was coming out. So it's just a simple matter, of scaling everything up to try and get to X-rays. And if you want to make it better, you have to try and make the beam brighter. There are lots of things that you can try and do. But if you look at that tiny little machine, you can see in this schematic that the same kinds of things are there. There is a source of the electrons that's over here. And they get accelerated in something called a linear accelerator into a smaller ring, which takes those and it ramps them up to a higher energy. And then you put them into this storage ring. So the storage ring is what accumulates bunches of electrons. You basically try and pile them all up in there. And the interesting thing is that when those electrons are forced to change direction, it's just like kind of on an antenna. They radiate and they make light, which you can use. And then we have these beam lines, which actually can modify the characteristics of the light when they come up, select parts of it or try and focus it. And then there are researchers who actually use that light to try and examine material properties. That's kind of a simplified version of it, but in fact, that's exactly what the earlier machine was like, and that's what the one that I'm going to tell you about, NSLS-II, is like. It's all a matter of scale and size and the characteristics of the machine. So you basically, that's all known. Okay, so good. Now I have light, but actually X-rays is kind of what I'd like to be aiming for. Everybody's seen that picture too, right? That's one that's fairly common. You know what you can do with X-rays. You break a bone, you go to the doctor, but in fact, Conrad Röntgen studied this and he took pictures of it in 1895. This is actually his wife's hand, a radiograph, and he won the Nobel Prize in 1901 for physics. It was the first Nobel Prize in physics for the discovery and explanation of what X-rays were. Turns out he wasn't the only one who was working on this stuff. At more or less the same time, it turns out our friend Tesla was busy working on things. He was actually looking into vacuum tubes at the time. And kind of as a secondary thing, he realized that there was visible light that came out of them and what he called black light, and then something that was very special radiation. And it turns out this very special radiation was X-rays. Tesla being Tesla, he was working on that. He learned what he wanted. He was getting kind of bored with it. So that radiograph he sent off to Röntgen because he heard this guy was working on X-rays and he was interested in those things. So true story, documented. You can go and read about it if you want. Our friend Tesla was not great at promoting himself, but he seemed to be a well of great ideas. Okay. Now I've got X-rays and radiographs. Those are certainly nice, but what else can you do with X-rays? Turns out that you can have the interaction of materials with X-rays. One of the things that can happen is something called diffraction, something known as Bragg's law, that in regular lattices tells you something about how if you illuminate something with X-rays, if they're the right wavelength, they can actually come out in little spots. So it's a way to actually analyze underlying structures. So another thing that you could imagine is looking at different materials. Now, certainly if you look at these in the visible, these two things are really, really quite different, right? But they're both carbon. They're actually both pure carbon. One of them happens to be diamond. The other happens to be graphite. And at the bottom of the screen, you can see what the crystal structures are. That's very easy to see with X-rays. Not so easy to see why they're different if you were just looking at these things in visible light. That's the kind of thing that you're going to hear a little bit about in event 40. I think that's sort of Jean's bailiwick, is looking at diffraction in structural materials and elucidating more than just sort of why diamonds are a girl's best friend and why graphite is what's good for batteries. Now, you've all seen this though, I'm sure, right? Diffraction is something that's pretty popular and has been for a long time. That particular picture that's on the middle of the screen was sort of like a seminal event in modern biochemistry. It was actually taken, it's a famous photo 51 by Rosalind Franklin. It was taken in a laboratory at King's College in 1952. And a number of other people actually ran off with that picture and got themselves a Nobel Prize for understanding what the structure of DNA was like. So this turned out to be a useful sort of tool even in biomolecular structures. Fast forward a little bit further and you can see here's a map of a biomolecular crystal, and they look at electron density on it. This is a little bit more like what Bob works on. And so you'll hear a bit about that too, I guess. And he can try and explain to you much better than I could how it is you can actually go from a diffraction pattern into understanding in exquisite detail the structure of biomolecules. Okay, that's great. Now I know how crystals work. I know how to do diffraction. What are some other things I might do? I could do spectroscopy, right? X-rays come at different energies, so I can try and do different things with those. And so you see here, if I have the X-rays and I've already learned what a crystal will do in terms of diffraction, in this case, they've got an X-ray tube and they illuminate a sample and it makes characteristic X-rays that come out. And you use this analyzing crystal. And so what you do is you move this detector around looking an angle for where the spots show up. And when you see those spots, oops, there we go, you'll see peaks in intensity at different angles. And if you know what those are, then you can actually turn it into characteristic spectra. You can understand what elements were in there. So I'm not only understand in that material what its structure is like, I understand what's in it, which is kind of a neat thing to be able to do. Now, again, I'm going to fast forward a little bit. These are kind of the laboratory setups, and you can go and find those on Wikipedia. But if you just go down the road from you, that's what it looks like these days. If you go to NSLS-II, you can use a beamline called the submicron resolution X-ray microscope. And you can use a technique that's called X-ray fluorescence. And when you do that, you can actually take advantage of the fact that it's spatially resolved, so you can see what it is. And this little bar down here is telling you that this is only about 100 microns. This is a bit of the inside of a plant. And in this case, they've tuned it up so you can see where the manganese, the iron, and the zinc are. That turns out to be an important sort of thing, not only for the biology of the plant, but there's also things called phytoremediation. People find stuff in the dirt that they would rather wasn't there, so you can plant plants that try and pick it up. And this is a great way to try and look at it and find out where does it actually find itself in the plants, so that you can decide, okay, do I just take the flowers? Do I just take the leaves? Do I have to dig up the roots if I've done phytoremediation, and decide which parts of the plant that I have to get rid of? So this is hardly an exhaustive view of the kinds of things that you can do with X-rays, but it tries to take you from some of the things that you should know pretty well into things that are maybe a little less familiar, but are made possible by having such an amazing source. So let's put it in the neighborhood, right? The National Synchrotron Light Source too, which is basically my part of the neighborhood, is down here. And the size of the font is kind of related to the size of the object. So the original NSLS is this little building over here. So I often talk about NSLS-II not as 2, but 5, because it's actually 5 times the circumference of the original one. And of course, in bold font up here is the relativistic heavy ion collider, which will be the future home of the electron ion collider. And it's rather larger. But that gives you some sort of sense of what's going on just from an aerial view of what the campus looks like and the relative size of NSLS and NSLS-II. So kind of in the middle of this project back in 2011, we were thinking about the differences between these and how do we try and explain them to people. And so at that time, we had this slide that was talking about NSLS, which had been operational since 1982. It had won 2 Nobel Prizes. People who had done work there had gotten 2 Nobel Prizes at that point, neither of which had anything to do with why we built the facility in the first place, I'd like to point out. But it was a very busy, very happening place, but it had been upgraded over the years and was basically at the end of what could be done in terms of upgrading it. So we were well underway at that point in constructing this newer, bigger machine. And we've already talked a little bit about it, but that was kind of what we were thinking back in 2011. I'm using my Wayback Machine here again. So why do you want to build it, right? You just don't make it better for the sake of making it better. You want to actually do things. Back in the days of yore, when I was a postdoc and I was measuring things, everything was sort of, how do you say, prototype kinds of experiments. I was very interested in catalyst chemistry. And so catalyst is stuff that you might use, say, like in your car. And it's sitting there cooking along, it's hot, it's, gases going on, there's a lot of pressure. So what was I doing at the synchrotron? I was looking at single crystal aluminum in an ultra high vacuum with a tiny bit of oxygen on it, because that was pretty much what I could look at. What we really wanted to do was to get to where you could look at real materials as they're really doing their work. That's how you learn about how these things go. Certainly the model systems were great, and we did learn an awful lot from those. But when you come down to it, there are some practical differences between ultra high vacuum and a couple of atmospheres of pressure, and things that are done at low temperature, even liquid nitrogen temperature or colder, and stuff that's happening at 2000 degrees Kelvin. So you need to have a better instrument in order to try and do that. We were also at the time kind of excited about nanoscale materials. There are a lot of things that change in the way that materials behave when they get small. But in order to look at them, you need a better microscope than we could have with the original NSLS. And so we wanted this highly optimized source that would deliver really bright beams so that you could actually look at things. And of course, if you're going to make a really tiny beam, it has to be really stable, because of course, if it's a tiny beam and it's waving all over the place, it kind of looks like a big beam. It's not very useful. So the stability, the stuff I mentioned that Nick had to do, was a real part of it. So this kind of set as a point of departure what were the things that we needed to do. But the real reason that we built it was because the research that it was going to support, and we were all done. So we worked on this. And lo and behold, this looks a little bit like the cartoon that I showed you before, right? It has its LINAC, it's got its booster, and here we have this big storage ring. And as I said before, even though it's called NSLS-II, it's broken into 5 pieces. There are 5 pentons. And this little booster ring that's here, that's actually the same size as the original NSLS X-ray ring was. So it was quite a bit larger. And it's sort of this paradoxical thing. And I love to do it when I get to talk about it when we give tours at the laboratory. It's easier to see there. Oddly enough, when you want to get small, the machine has to get big. It just winds up being the way that the optics and everything works out. So this is why we wind up with such a large machine, so that we can get to these tiny beams. We have some instruments that can actually make beams that are on the order of 10 nanometers and smaller for the microscopy that they do. So you can talk a little bit about what were the kinds of things that are inside of it. What's the scope of what's there? We built this storage ring. It's almost half a mile in circumference. We built all that, the electron machine stuff, and we built experimental facilities too. The suite of 7 beam lines was what was originally in the project, although we could host up to 58. And all the conventional facilities. It was a big, huge building campaign that had to be done. And there was some research and development that had to be done in order to try and make that go. So to get some feeling for what the size of these beam lines are like, right? Well, let's start here. This is the storage ring, and there's that little tiny booster, but to give you some sense, this is 800 feet across. So for those of you who are fans, you could go to Yankee Stadium, you could drop it into the middle of this infield and walk all the way around it, no problem. The beam lines, you can see they're actually inside of the machine. This is 77 feet wide, but they come off at an angle, so they can be quite long. So you see on the floor here, we have these little tricycles. The building is so big, it's half a mile around, that we ride these tricycles around because it's easier to get to and from where you need to go on those. And inside of the machine is row upon row upon row of these magnets. That's actually what conditions the beam and what steers them. That's a whole story in and of itself. There are over 1,000 magnets that are inside of the machine that steer the beam around. So here's the building part as it's going up. And you can see going from January, we had just sort of scratched the dirt in 2010. By August, you can see the building beginning to come up out of the ground. By April of the following year, this is 18 months later, give or take, it's really beginning to take shape. The roof is going on in some parts. By August, it almost looks enclosed of 2011. By April, it looks almost as it does today, although there were a few little details that hadn't been filled in. And by 2013, so this is from 2010 to 2013, this big giant building is there. That's a lot. That's a lot of construction to be going on, and it's a lot to try and keep track of. At the same time, there are all these things that we were going on. We talked about the LINAC and the booster and the storage ring you saw. There are these very special kinds of magnets that actually increase the intensity of the X-rays that we get, called insertion devices. That's a topic for a whole day if somebody wanted to talk about that in event number 40, whatever it happens to be, Neil. And so it was really important in all of this, though, that it was an integrated design. Everything has to work well together in order to actually do what it needs to do. And of course, this is just on the accelerator side. All of this stuff is supposed to go out to beam lines. So here's that tricycle again. And sometimes, again, it has to be very long to get to very high resolution. This is part of a small angle scattering instrument. It needs to get very long so that they can look at small angles, but still spread them out over a detector to try and read. This piece here is actually a special chamber in which there is a microscope. This is the one that has the 10 nanometer X-ray beam in it. And up here, we'll come back to this. This is an X-ray machine that has a robot for actually changing the samples around. And I'll kind of explain a little bit about why that is, because at least initially, when you did these things at National Synchrotron Light Source 2, or even some of the predecessor ones, you have to put your samples, X-rays anyway, inside of a room, and then you close the door, and then you can turn on the X-rays, and you can do your measurement, and away you go. And in my younger days, you would do that, and that was fine, because you would just close the door, go off, have dinner, come back, you'd measure something. But we have this new, really, really potent source, and so it generates so many X-rays that the samples don't take even a second to measure. And so if you're spending all your time opening and closing the door, you're not doing very much measuring. So in fact, this robot can pick up samples and put them on that spectrometer and measure them, and then pick them up and put them back into a suitcase. And somebody realized once that was done that there's no reason you couldn't put samples that were slightly radioactive in there. Because after all, the robot doesn't care. It's perfectly happy to pick those things up. So in fact, there's been a huge bunch of work that's been done to try and look at samples that are related to nuclear reactor technology. They're looking at materials that are in reactors to try and make sure that they're not going to fail. They're looking at fuels to try and see that they're going to be okay. So that turned out to be, I think people kind of understood as they were building it that this was going to be something that was possible, but it's really worked very, very well. Another kind of thing that you can do, because you have a lot of X-rays, is something called tomography. People have heard of CAT scans, right? CT scans, you go get medical imaging, and they really are X-rays, and they just look at a bunch of different angles, and so they can see what's going on. But with one of the beam lines that we have, which is a full field X-ray imaging microscope, they can get down to very small. They can do 30 nanometer resolution on 100 micron field of view. 100 micron is on the order of the width of a human hair. And what's neat about this, if I get out of the laser pointer thing here, is you can actually look at the sample as it's sort of spinning around. So you can see that, that's kind of neat. But the sample is actually a piece of copper, and it's sitting inside of a solution of silver nitrate. And in just a minute, you can see these little things that are kind of growing off the side there. These dendrites are beginning to form, and it only took a minute for them to do that. 2 minutes later, they're getting even bigger. And at 3 minutes, it's beginning to look a little bit like the Shoreham Village Christmas tree. This stuff is kind of neat to watch. It's also happening very fast. That's why it's good to have these X-rays, not only for the resolution, but for the speed. And that's great. It's nice, it's show and tell, but why would you care? Any of you got a cell phone? Any of you ever had a cell phone battery die? This is exactly how your cell phone batteries die. As they cycle, there is growth that goes between the electrodes and it makes them short out and they fail. And so being able to see how this grows, being able to actually modify things, I mean, this is just a demonstration so you can see it. But that's the kind of real practical problem that you can try and look at when you're using the kinds of instruments that we built for NSLS-II. So there's a way that you get there. You can kind of navigate, right? We're going to go into kind of project land for a little while, and there are all of these milestones, and you can get this list, and it'll tell you all about what it was that we did. We started in 2005. They said, yeah, we got to do this. And then you go through a series of things where you get to 2009. They say it's okay to build it. Go ahead, start building it. We do a number of things, and we say we're all done in 2015. You know, this list is okay. It's kind of a way to navigate. But I always found these sorts of things much better. These schedules that you make were much easier to try and see what was going on. So what you find here, if you work with this, is you have sort of these critical points that I talked about, the big decisions. But you also get to see in here, here's how the design progressed. Here's how the construction progressed. Here's how it turned on. And this red line, we always love to talk about this. This is the critical path. That's the thing that makes it so you can't go any faster. So you can think of this as a schedule if you'd like, but it really turns out to be a communication tool. And it turns out if you're going to do a big project like this, that's what it's all about. And so it turned out that it showed what was supposed to happen. It told you where the milestones were. It told you what the critical path was, but it's really a stakeholder communication tool. Everybody can kind of see where they are on the map, but in this case, the map is by time. So as Neil said, at the end of the project, I was the deputy director, which means I got to do all of the sort of closing out the project and all that fun stuff. And so one of my favorite slides was this one. We have these things that we're supposed to do. They're called key performance parameters. We had done that by October of 2014. Here's what we said we were going to do. This is when we did it. And in every case, we actually exceeded all of those KPPs. Good for us. That was great. And I love this slide because we exceeded all of these things, but also because sort of wryly in it is communicated one of the things that actually was one of our issues through the whole of this. Over here, it says rather cryptically that CM2 was received on 21st of November 14. That's a cryo module. That's an RF cavity. Basically, we got it. We checked it out. The federal project director, a guy named Frank Crescenzo, wrote off to the AE, who is the acquisition executive, who was Harriet Kung, and said, they're done. And she said, good, they're done. That's how it actually happened. But this was great. I mean, Jim Rose, who's in the neighborhood, one of the best engineers I've ever met, he came up with this. He says it's Sisyphus revisited, because the RF cavity was just like that. You'd push it up the hill, something would go wrong, it would come back. You'd push it up the hill, which was wrong, it would come back. So certainly for those of us who were involved in it and saw it going on day by day, that had a lot of good messages in it. So it was communication in a different kind of way. This is one of the favorite slides that I use when I talk to people about these projects. And generally, and I have this in my office, anybody who's been there has seen it, is the single biggest problem in communication is the illusion that it has taken place, from none other than George Bernard Shaw. And that's certainly the case. How many times have you been in a conversation and people are like this? Yep, 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 I get it, I get it, I get it. And then you go and you ask them about it afterwards, and it's like there were 5 different meetings that were going on. Nobody somehow or another, it didn't happen. So it's a real art when you're trying to do these things to understand what it is people want and then ask them enough times that they can explain it to you. Get it to the point where you can explain it to your mother, because at that point you probably understand it well enough. And so by way of a flashback, I'm going to talk a little bit about at least an episode when I was involved in some of the technical specifications for this. So again, it's a big thing, right? This is $1 billion. It turns out that the power coming into it could be as much as 20 megawatts. We typically only use 7 or 8. But that's a lot of power. Where is it going to go? So this was the utilities planning, and we were trying to figure out how to make this work. also tell you a little bit about the way that we designed the tunnel and the conventional construction. But on this is the ever popular, ever deadly spreadsheet, right? People write things down, they try and calculate stuff. If you look down at the bottom of it, here's a bunch of notes that I took on, you know, what was the chilled water system, what were the process loads, all that sort of stuff. We had to gather all of these requirements together and try and reconcile them. And so that's a lot of meetings, that's a lot of conversations, but how do you go about checking it? Well, I'm a picture sort of person. So that's what we generated in the end. It's a little cartoon, and it might be regarded as cartoonish, but on this is the energy balance for the entire facility. And at a glance, anybody who knew what they were looking at could look at this map and say, oh yeah, okay. So there's almost 9 megawatts that's going into the facility, and the air conditioning is taking out 1 megawatt. The processed water is taking out 5 megawatts. The processed chilled water has got to deal with 2.5 megawatts. Things are actually going back and forth in between. Okay, here's the synchrotrons, the storage ring RF. There's a cryogenic system. It's actually liquid helium. That's a scary thing. And so there's some heat that's generated by that. It puts power into the beam. And that beam power could actually go from here, or it could go as to heat into that system. So it actually shows you at a glance all the places where the energy could be going inside of this machine. I can show you that 45-page long spreadsheet, and you're never going to figure it out. You look at this map, and you're all experts already. You know exactly how it goes. So it turned out to be a useful sort of exercise, because once you make a map, once you make a picture like that, it's easy for people to look at it and check it. They can understand whether you understood them or not, and we can try and get the requirements right. And getting the requirements on something like this is important. There's another famous Buckminster Fuller thing that says that if you make a change in plans, all you need is an eraser. If you make a change in the field, it requires a checkbook. And we didn't want to waste any money. So, oops, here we go. I'm still learning how to drive. Here we go. So I've just, in this yellow box, sort of told you a little bit about the things that were there. Is, you know, we took this idea of collecting up a bunch of information and turning it into a map that was sort of easy for everybody to navigate. And it turned out to show up in all kinds of places. This is another sort of personal favorite. And in fact, that is me at a whiteboard drawing what the tunnel should look like. And so Andy Broadbent and I and Ovi Dialing, our dear friend Ovi Dialing, who's the architect on this, he whips out his phone. This is 2008. What do I know, right? I didn't even have a cell phone at the time. And he whips out his phone. Oh, this is good. I got to take a picture. So this is a picture Ovi Dialing took on his phone. And so you can see here what we're doing is we're trying to say, okay, what should actually be in the tunnel? Where can you not put anything? Where is the machine going to be? Where are the beams going to come out? What's the stuff that's hanging on the ceiling? So we made a picture to try and make sure that we understood what we were talking about to each other. And not 6 months later, the architects had turned that into a plan, which that's pretty cool. And we could check it because we knew what it was supposed to look like and all the dimensions were right and things like that, which was pretty good. Not terribly long after that, it's real. And I have to say that that kind of thing happened over and over again in this project, right? Where we dreamed something up, and it's quite one thing to have a picture in your head, but then to go walk inside of this giant thing is really very different. It's exhilarating, and it's just strange, right? To see something like that come off the page and become real. Now, it took 2 years to go from that whiteboard picture to where it was in concrete. And that's actually amazingly fast on the scale of things. And I do want to point out here that these CF is for conventional facilities. The errors and omissions on this project were unbelievably small. Conventional construction, it's not unheard of to have sort of 15 to 20% errors and omission costs. The NSLS-II project, it was under 5. And part of the reason was that we knew screwing up was going to cost us a ton of money. And so we paid extra attention to trying to make sure that it was absolutely right. The reason that mattered is at the peak of this project, we were spending $1 million a day. And so you can't really be stopping and scratching your head and thinking about things because you can just hear the cash register going at $1 million a day as you're making mistakes. So we were not interested in being the people who wasted money, and that served us well. So not too terribly long after this picture was taken, really, all of, there's a machine that's in there. So the next question you got to ask yourself is, okay, did this just all materialize and then we finish the building and then all of a sudden you fill in with this machine and it's only 2 years? Actually, people were a little more clever than that. Because the machine is so big, they were actually building parts of the machine, the building, and once a piece of the building was done, then you could actually go in and start putting the machine in it while people were still building the rest of the building, which is not the way that it's normally done, but because it was so big, we were allowed to do this. We were able to work with the contractors to do it. So up here, piece by piece, it tells you when the beneficial occupancy was for the building. And down here is how the installation went. And so if you could read that, I don't know if you can actually see it or not. It wasn't terribly long after we got into the building that we started doing the installation, and not terribly long after that that we finished the different pieces. And so that allowed us to move along very quickly. And we had, really, again, thinking about how it's actually really going to work. It's fine to just sort of say this little piece about how it's supposed to happen. But this is some of the detail that goes on into how we actually move through the building. We had to actually cross through pieces that the conventional construction people were already working on. So there was a very detailed plan. And again, remember that touchstone we had in 2011, how we thought things were going to work? This is the actual building under construction. And so you can see this part here, it looks kind of finished. Over here, the roof is on, but the walls aren't even on. Over here, there's steel. It's not even got any of the stuff on the outside of it yet. As this is going on, we're already installing accelerator on the inside. And so this is one of the things we had the luxury, because it was such a large site, of going this fast and doing all of this stuff in parallel, which was great. So we had to keep planning. This is, again, 2011, and we're looking at the benefits of this thing. And so we're planning not just for operating what we had, the NSLS, but building the NSLS-II, operating the NSLS-II, building more beam lines. We had a very full plate of things that we were thinking of in 2011. And so as we went on a little further, we were talking about, in 2015, this is when we had finished building the project and what we expected the next few years would do for us. And people thought we were crazy because we said we were going to have 28 beam lines in operation by 2020. That's roughly twice as fast as anybody else has ever built one out. And it actually turned out that way because we planned and we understood what we were doing, and these things take a while. But what's really kind of fun to look at, for me anyway, is here's where we first turned it on. It was actually in October of 2014. This is when we first turned beam lines into general user operations, and there's been this steady growth that whole time. Right now, we're kind of in a lull. We have another beam line that's under construction that'll be coming along in a while. We've just started another project that's going to build 3 more. We're working on a project to try and fund some more. So there's a long induction period for these things. The NSLS-II project, really, if you want to think about it, started in 2000, although it didn't officially start until 2005 when we got permission to make it go. And then it took 10 years to actually execute it. So these are things that take a while, and you have to plan and you have to be ready to adapt. So great, we've got this all built up. We're only actually halfway done with the beam lines that we mean to build. But remember, we were going to build this because we had some benefits. The construction project, fun and achievement that it was not for its own sake. It was so that you could actually use it. So there's some benefits that you want to try and realize. And this picture sort of summarizes what's really only 5 years of operating history in the machine in a very nice way. There's some things up here that are called new beginnings. So we had the first joint users meeting with the CFN. We had some proposals of a new type, beamline access group proposals. These are all things that are kind of for, the insiders. This one's actually a little more fun to see. These are the beam lines as they're building up. How many are in operations that users can come and use? So we started out with 5. It's kind of like a clock. It's like a dial gauge. It's filling up, right? And so it's about halfway full. There's another characteristic of these machines, if you're sort of an insider, is what's the current they run at? That's how much power do they have? And you can see that's been steadily climbing. Some things related to user operations. In just 2 years, we had already had 1,000 people come and use it. 5 years out, 3,300 different unique people had come to use the facility already, only 5 years into operations. We got our first paper from this thing in 2015, the first year that it ran. We now have accumulated in 5 years 1,000 papers. And these are peer-reviewed papers, and peer-reviewed papers means that somebody's actually read what was produced and believes that it's correct. And then there's sort of another metric that they have for publications. They talk about premier journals. In other words, ones that are highly cited, that are read very often or considered very influential. It turns out nearly a quarter of the publications that come out of NSLS-II are in these premier journals. So in a very short period of time, it's become an extremely impactful tool, which is just the kind of thing that we'd envisioned it to do. Oops, there we go. It stopped. No, let's go back. So we've ramped all this stuff up. You can see all of these things. These little 3 letters in here is an alphabet soup of names that says what each of the beamlines happen to be. We have one which is commissioning, which I think may this month actually go into general user operations, and this other one I told you about in construction. Fastest ramp up anybody's done. This is again another kind of a map picture, show you how things have turned on and how we've been running. And we've had some adjustments that came because of this little virus problem that we're dealing with right now. And that's actually seen here where we talk about our users. This is how many people come per year to use it. And we were on a good track for 20, and then March came, and so we had to slow down. But even so, there was almost 1,300 users who had used it. And this is the rate at which the publications are happening. Last year, we had the equivalent of a publication per day from the user community. So it's a very impactful sort of thing. Now, one of the reasons that it can do that, of course, is we wanted to do real materials and how they actually do their work. And we wanted to actually see from that people didn't have to come and just use one experimental apparatus. They could use multiple experimental apparatus. They want to use multiple beamlines to try and solve their problem. We call that multimodal use. And this picture here gives you some insight. Again, it's kind of a map and it's kind of fun. It's a word cloud over here of the words that showed up in the title of proposals that got beam time since 2015. Structure is pretty big. In situ, in other words, looking at things as they're actually doing their work. Those are big things. Materials are big, catalysts are big, batteries are big. And they use a host of techniques. It turns out that X-ray absorption spectroscopy or small angle X-ray scattering, just a whole alphabet soup of techniques, which would take days to explain all by itself. But you can see that there is quite a range of things that are possible. And this one here, this little map that's in here is kind of really telling you the story that people actually do use multiple beamlines. These little letters on the side are the names for each of those beamlines. And if a particular proposal went from one beamline to another, or sometimes 2 or 3 beamlines, you can see that very easily from this map. So without actually getting into the details of what the specific measurements are, you can see it's working, at least qualitatively, in the way that we'd imagined. There's a lot of science that's being done over a range of things. People are using the full suite of techniques that we have, and they're taking advantage of the fact that we have put in place things that allow you to coordinate data between different machines, different beamlines. I will take a moment to say we did have this extra little adventure that came along. I'm giving this by Zoom now instead of giving it to you in person in March. And it turns out that we are ideally situated to make important contributions to this. I'm usually a little bit reserved about these sorts of things, but in this particular case, I can say without fear of contradiction that we have the best beamline for this purpose in the world, bar none. There is no question. This one can look at crystals that are 200 times smaller than anybody else, 200 times smaller. Now, why does that matter? Well, you're in a hurry. If you want to solve a crystal structure, especially in these protein structures, and you've got a lot of time on your hands, you can grow a nice big crystal, but you're talking about years. We don't have years. People are growing these tiny, tiny little crystals, and they need these structures. It's important. It's life or death kind of important to be able to do this kind of work. And so even in the COVID crisis, people basically came in, ran these particular beam lines. We ran nothing else. They ran these beam lines so that they could actually make structural measurements on things that related to COVID. And Bob can tell you all about it in his next talk. Presumably there are going to be some really good things that come out of that. But this has already done some very important things, because what they were able to do was, in this example, they're talking about measurements where you can actually look at drugs that are already approved for uses, but different uses, computer models that said that, oh, that drug might actually work on nesting in with COVID protein. And now you can actually take for different parts of the proteins. We don't do any live virus that I'm aware of. But you can take those drugs and those proteins, put them together and try and see if it actually does what you expected. Does it nest up? Does it match in the way that you'd expected? That's not something that we had imagined we were going to be doing when this was all built. Certainly nobody was dreaming about COVID, but that's the importance of having a flexible and powerful tool in bringing it to bear on problems that really matter to people. And we're all very proud of our ability to do that sort of thing. So we're really trying to deliver on the promise of those instruments that we had, and are working hard at trying to build those up and make them useful to people. And of course, nothing lasts forever. This machine is already now 15 years out of the imagining. So we're looking at sort of 2030 timeframe, thinking about upgrading it further. You want to stay at the forefront of things. And so right now there are active plans in trying to figure out how we could make it even better than it is. So that's part of an ongoing thing that will go for a long time, I'm sure. So with that, I'm going to just sort of set that table and point you to the upcoming event, which is in December. It's Gene and Bob's Most Excellent Adventure. I added the most, and I hope it was a most excellent adventure. And they will tell you all about the kinds of things that they're working on. What were I a resident and permitted to do so, I might very well want to come and see it myself. But for now, I'll bid you adieu, and with this thought that you can really dream of these things and you can make them come true. It's just, takes putting one foot in front of the other. And for me, this is one of the best pictures that came out of NSLS-II to NSLS. This was actually on the day that we got first light from the NSLS-II, that building over there. That's NSLS. And there was a wonderful rainstorm that was going on and a beautiful rainbow. Our friend Roger Stoutenborough ran around like a madman and he took this picture. And to me, it's sort of like the light going from NSLS over to NSLS-II. So thank you. Any questions? I haven't been watching the chat.
We have questions. We have things in the chat. But
Okay.
I want to say thank you. And I want to say we'll make, with the approval of our president, I believe TSVA and invite you to this talk as a special guest. I'm asking the president right now whether that's okay. This is the important one, not the other one.
Oh, jeez.
Okay, too, but she's the one relevant.
Well, I certainly second that. And I just wanted to say that the chat room does not have specific questions for this talk. And although Sal said that it's great, he had to leave early, but he thought it was fantastic and he's looking forward to the recording.
All right.
I had a question. I want to know if John Miller works on this device.
Oh, you can talk.
I don't, but I have a different question.
Okay.
Early on, a distinguished gentleman, might have been Erik, might have been Neil, said that Erik had to consider the movements of oceans and maybe other large objects in designing this machine. Erik, could you comment on that?
Yeah, that was actually Nick Simos who figured that out. And it's amazing how sensitive this is to noise. We can actually see the waves breaking on the South Shore in the vibrations that are in the machine, but we can actually damp them out and control them. And it kind of defies your normal sense of how sturdy things are and how much motion actually matters. That ring is 800 feet across, 800 meters in circumference, give or take. We know where everything is in that ring to 100 microns. And it matters because we're steering a beam that's good to about 10 microns. They recently figured out exactly why they were seeing some noise in the machine, it turned out that we can actually tell you what the phase of the moon is by looking at the RF frequency. The phase of the moon changes the circumference of the ring slightly, and that changes, when the circumference changes, the frequency to get the beam to circulate has to change. And so we can follow it. I mean, it's just amazing, these things that you would never think really matter become important when you're trying to make beams that are this small and this tight. So yeah, everything does count.
I have another question, Erik. Can you tell me how much work is going on for COVID-19 at the NSLS-II?
So at the moment, we're now at a state where we don't have everybody in. It's sort of about 65% of the staff can be on site. There are people like me who can actually do most of their work from home. So in order to keep the density of people on the site down, we stay home and work from home. I believe each beamline is up and running now. We're not.
I guess my question is more in the spirit of, are people pounding at the doors to get access to beamline run here or not? Are they keen to do it?
People are trying to get samples run, but what we're doing is running them remotely for most people. So you can, on some beamlines, you can send us a sample and they'll run it for you. Or in a few instances, like the biology beamlines, you can actually run it remotely. They've invested enough in the controls and so on that a researcher at a different university can actually steer what the beamline is doing from their own laboratory. And in some very rare cases where it's absolutely necessary, we've now started allowing users to come one at a time, one only per beamline, because we're trying to stay, socially distant and try and contain this virus. We'd love to have more people come. We were, like I say, we were on track to have 2,000 people, and it's interesting. It is a people business. It was really designed and centered around people being in a social environment. And that's actually one of the often overlooked contributions of a facility like this, is that the people interacting with each other are what drives science forward. And that's been challenging for us, because it used to be you would see somebody at coffee who does something completely different than what you're used to thinking about, and it would kick you off in a new direction.
Right.
I used to talk about NSLS as being at its most powerful when it was broken and the power was off. And that was because you would be forced to go out to the aisle and you'd have to talk to people, and often they were interesting people and they had good ideas.
That's why you go
so, even in the design of NSLS-II, we paid a lot of attention to trying to make sure that there would be sort of social massing. Those buildings around the outside are clumped together for a reason. It's not just that we can bring beamlines out in between them. It was because each of those buildings by itself is about the same size as the laboratories and offices that were in the original NSLS. And so it kind of makes for its own critical mass of people who interact with each other.
What I'm trying to ask you is, does Brookhaven, or should Brookhaven, try to alert people at the Center for Communicable, whatever that thing is called, diseases, to the use of this thing? Maybe they don't know how
I think they are well aware of it. There is something called the National Virtual Bio Laboratory.
Yeah.
And there has been coordination across a bunch of laboratories and a bunch of disciplines who are doing COVID research on all kinds of things. There was a workshop just a week ago, I think. And there were all kinds of interesting things that were in there, and not just what you would imagine. There was a whole section there, people looking at N95 mask material. What are good masks, right? Not the sort of thing you would think of, but for a machine that can do materials characterization, that piece of it at least is a walk in the park. So it has, a wide range of potential applications, and it is very well known. It's the world's leading light source at the moment.
So we have a question from Joe Falco. Do you want to unmute yourself?
Yes. Well, first I just had a comment, and then several comments and then a question. My comments are kind of about you, Erik. through the years, I've had the pleasure of getting to know you so well, and it's just a marvel what you and your team have been able to put together in terms of the whole NSLS-II, and it's a tribute, I think, to your brilliance and your organizational skills. It always mystified me how someone so nice could pull off such a giant and complex project and do it under time, and I think that it's a tribute to your.
I have a lot of friends, and I'm along for the ride. They let me ride along. There are all these smart people who let me hang with them. It's great.
Absolutely. Well, I think it's a tribute to your interpersonal skills and your sense of humor. You touched on the people in the village who have been involved in this, and you mentioned Bob work there, and I wanted to actually cite other people. Of course, Tim Savage is really the picture and overseeing John Hill and the light source too, and in the audience too is Laura Miller. Laura, I think we and oversaw a whole bunch of administrators. Like admin support for projects like this are really important too. So definitely want to acknowledge Laura, and I'm sure I'm leaving people out, but I just wanted to mention one other thing, and that was today I was at Shoreham Plaza, and who was there but Yanni Van Steenbergen, and of course Yanni Van Steenbergen is the widow of Ari Van Steenbergen, who really was the person who built or oversaw the construction of Light Source 1. So it's kind of coming, you might say, full circle, and to have seen Yanni and thinking about Ari, and then to see you here today, Erik, which was just wonderful. So I'll end all those. I'm sorry, all that wind with just a question. Just have a very modest question. I noticed on Light Source 1, which of course is this tiny thing compared to Light Source 2, that they actually had two rings. One was an X-ray ring, and the other was an ultraviolet ring. And I was just wondering about that. If you miss having ultraviolet, or if you can tune it to do ultraviolet, or there's tricks to do infrared or whatever. Could you comment on that?
Absolutely. So that is actually a calling card, and thank you for bringing it up. That has been a calling card for NSLS and is for NSLS-II, is the wide range of energies from the infrared all the way out to very hard X-rays. And when we designed NSLS-II, it is indeed just one ring, but we took great pain to make sure that we could do all of that. And so we've commissioned now just a few infrared beam lines. We're working on a hard X-ray beam line that will make 200 kilovolt X-rays and everything in between. And so the original one, it did have two rings. The lower energy ring, it was easier to make UV light. It was easier to make an awful lot of X-rays. But it turned out when we went through and we're doing the design trade-offs, even though we considered making a two-ring circus, in the end we decided that we were better served by having a single ring and taking advantage of the stability, essentially investing more heavily in the one ring and making it perform really well across the energy range. So yes, the NSLS-II, and if you looked at that map that showed all the techniques that kind of cross across the different beam lines, they ranged from, in that case, it was soft X-rays all the way up to hard X-rays. Great question. Thank you for asking.
Erik, before the next question, it was suggested by somebody that you might want to unshare in case.
Oh, sure.
So that we can all see each other talk.
I'm sorry. I should have done that right away. I apologize.
That's okay.
Let's see if I can do that. That's this button over here.
Okay, and then our next question is from Carrie Mirabella.
Hey, Carrie.
Hello. Hi, Erik. How are you?
I am fine. And yourself?
I am well.
Good.
I have a question not regarding cost and schedule, which is my usual question.
Yes.
You had mentioned in one of your slides or your voiceover about plant-based research.
Yep.
And I did not write down, it was phyto something, but I just
phytoremediation is one of several plant things that people are looking at.
Okay.
And so, as I understand it, you might have some site where there's a relatively low concentration of nasty stuff that you don't want, let's say chromium that's in the ground, and you'd like to pick it up. Well, if you dig up the dirt and you process it, that can be done, but it's pretty expensive. And often what's done with the dirt once you're finished with it is you have to haul it off and put it in a landfill somewhere. An alternative approach is to actually try and concentrate that stuff in at least some kinds of materials, metals, are selectively taken up by different kinds of plants. And so what they do is they plant these plants and it goes someplace in the plant. And that's part of what that research to do is to find out which part of the plant it goes in. So then you harvest those plants and then you can easily take those away, and it's much less expensive and easier to sort of concentrate those wastes from the plant matter.
Okay.
But that's hardly the only kind of plant research that's going on. People are using it for a variety of things. But it's particularly, the machine and some of the tools we have are particularly well suited for seeing where elements, metals in particular, distribute themselves inside of plant cells.
And being retired now, that's where my interest lies, in not how the projects get built, but what they're used for.
Mm-hmm.
And my own backyard, basically.
Absolutely.
Thank you, Erik.
Sure, thank you. Glad to hear from you.
Nice to see you.
Oh, do we have questions from anyone else?
Erik, why are you so good? Why are you able to give such a good talk?
Practice.
Right. Practice makes perfect.
It's interesting. I figured I didn't know how you people dress for this, so I put on a tie, right?
I thought about that.
It is the first time I've put on a tie since March, I think. But it just went on like that. And it's because when I was working, I put on a tie every day, and so it was practice. It's just a matter of practice.
Barbara?
Barbara.
I'd like to comment to Neil that Erik is not only wonderful at science and wonderful at speaking and wonderful as a personality, but he's also a wonderful singer.
Is that right? A singer.
Oh,
I can't wait until we can get back to that.
Event 41.
He used to be my group leader when I was a tenor at Liska.
What fun. Group 41, a concert by Erik.
Probably not.
I want to thank you again on behalf of all Baker's dozen of us who are left for your talk and kindness in doing it. Laura?
I would just like to say thanks for a walk down memory lane, Erik. It was so good to see you and hear you again and remember those times.
And now you're remembering why you retired, right?
You know, especially when you were showing some of the events that we had, and I'm thinking, wow, there was so much work that led up into that. It was so crazy, but a lot of good times and a lot of good memories. So thank you very much. And I'm very proud of it. It's quite an accomplishment for me too, to have played a small part in bringing that marvelous machine on.
Yeah, it was a lifetime event for a lot of us.
Yeah.
Thanks so much, Erik. Wonderful. Absolutely wonderful.
Thank you. Well, hopefully as your first Zoom victim, this wasn't so bad. And I know people are Zoomed out by now, right? Between that and helping the kids and all the rest of that sort of stuff, that on a nice Saturday, you could be persuaded to come and sit for this. I'm eternally grateful. So thank you very much.
I'm curious to know how many of you, I agree, would do this again. Is this going to work as an events program?
Yeah.
Yeah, sure.
Oh, sure.
It's all right.
Absolutely.
Excellent.
Glad to hear it. Let me just say one more thing. I used to be friends of the Tesla Science Center down the road, not far from here. And in my view, part of Shoreham. And I would see this guy out there parking cars for some event. He helped any way he could. He's amazing. He out there parking cars for people when they came to some celebration. So it's all around good.
So are you familiar with Thomas the Tank Engine?
But Thomas?
Thomas the Tank Engine? His motto is my motto. It's to be responsible, reliable, and really useful. So if you need to park cars, go park cars.
That's the spirit.
All right. Okay, well, thank you very much. And I will leave you for the evening then.
Thanks,
Enjoy
Erik.
the rest of your
Thank you
weekend.
very much, Erik.
Bye-bye.
Bye now.